So let's analyze the effects of a buffer solution and how we can resist pH changes. So I'm going to set up two problems here, one on the left and one on the right. The left is a non-buffered solution, so we're going to add one drop, or 0.05 milliliters, of 10.0 molar sodium hydroxide, and we're going to add that to 10.00 milliliters of water. What is the resulting pH? So initially, we have pure water. So that means we're going to start with a pH equal to 7. And now we're going to add one drop of our NaOH solution. So we have 10.0 moles of NaOH per liter of solution. We are adding 1 milliliter, which is 0.05, or sorry, we're adding one drop, which is 0.05 milliliters, which is going to be 5 times 10 to the minus 5 liters. So the amount of moles of OH minus we have is going to be 5 times 10 to the minus 4 moles of NaOH, but since it's a strong base, that's going to be the moles of OH minus. So our concentration of OH minus is going to be 5 times 10 to the minus 4 moles of OH minus per liters of solution, which is going to be 0.01005 liters, which would be the 10 milliliters plus the drop, which is 0.05 milliliters. And this will give us a concentration equal to 4.98 times 10 to the minus 2 molar. So our pOH is going to be the negative log of that, which is 1.30, and our pH is going to equal 14 minus 1.30, or the pH is going to be 12.70. So our change in pH is going to equal our final value, which is 12.70, minus the initial value of 7. So we're going to see a change in pH equaling 5.70 pH units. Okay, that's by just adding one drop of 10 molar sodium hydroxide to water. Okay, so now on the flip side, we're going to take this one drop of 10 molar sodium hydroxide, and we're going to add that to 10.00 milliliters of a 0.50 molar acetic acid plus 0.75 molar sodium acetate solution. So what is our resulting pH? Okay, so initially, before we set anything up here, we have to calculate the initial pH of our solution. And to do that, we need to use the Henderson-Hasselbalch equation, which is the pH is going to equal the pKa plus the log of A minus divided by HA. And the pH is going to equal the pKa, which would be the negative log of 1.8 times 10 to the minus 5, which is going to be 4.74, plus the log of the concentration of A minus, which is 0.75, divided by the concentration of HA, which is 0.50. If we calculate this out, our initial pH before adding any sodium hydroxide is going to be 4.92. So let's find out what happens to the pH when we add our hydroxide. So in this particular expression, we're going to add OH minus. Okay, that's going to be neutralized by the acetic acid, and that's going to give us C2H3O2 minus plus water. So when we're looking into these particular problems, whenever there's a possibility that the total volume is changing, we want to work the problem out using moles instead of molarity. And we often see this done in buffer problems because we're going to be adding quite a bit of solution to our buffer solution. In this case, we're only adding one drop just to prove a point, but a lot of times you're going to see a much greater value than that. So let's work this out instead of in moles instead of concentration. So we're going to have, before the reaction starts, how many moles are present. Then we're going to add a certain number of moles. we're going to have a neutralization reaction taking place, and then we're going to have our final concentration, or the concentration after the neutralization happens. So before we start this, we're going to have 0 moles of OH minus. The acetic acid that we have is 0.5 molar. We have 10 milliliters, so if you take 0.5 times 0.010, we're going to get 5.0 times 10 to the minus third moles. Same thing when we take 0.75 times 0.010, we're going to get 7.5 times 10 to the minus 3 moles as well. Okay, and we get that by taking the concentrations in moles per liter and multiplying by the volume converted over to liters. The amount that we're adding is we're adding 1 drop of sodium hydroxide, which is going to be the same number of moles as we added over here on the left-hand side, and that's going to be 5 times 10 to the minus 4 moles of sodium hydroxide. We're not adding any acetic acid or acetate ion. So when we neutralize this, we're going to need to neutralize 5 times 10 to the minus 4 moles of hydroxide. That will give us 0 for our hydroxide concentration. Okay? In order to neutralize that, we need to use up 5 times 10 to the minus 4 moles of acetic acid, and we're going to produce 5 times 10 to the minus 4 moles of the acetate ion. So when we subtract 5.0 times 10 to the minus 3 minus 5 times 10 to the minus 4, we end up with 4.5 times 10 to the minus 3 moles. And when we have 7.5 times 10 to the minus 3 plus 5 times 10 to the minus 4, we end up with 8.0 times 10 to the minus 3 moles of the acetate ion. Now, the reason we can do this is when we set up the Henderson-Hasselbalch equation, it's the pH equals the pKa plus the log of the concentration of A minus divided by the concentration of HA. It becomes very nice because the total volume at the very end is going to be the same for A minus and for HA. So our pH is going to equal the pKa, which we already determined to be 4.74 right up here, plus the log of the concentration of A minus, which is going to be 8.0 times 10 to the minus 3 moles, divided by, we'll say X liters, divided by the concentration of HA, which is 4.5 times 10 to the minus 3 moles, divided by X liters. So it doesn't matter how much of this particular solution we added, the liters right here are going to cancel. So this is why we can use moles instead of concentration in these particular equations. When we do this, we're going to get a pH value equal to 4.98. Okay, so if we compare our initial pH, which was 4.92, to now our final pH, which was 4.98, our change in pH is going to equal 4.98 minus 4.92, which gives us 0.06 pH units. So if we look at the effect of adding 1 drop of 10 molar sodium hydroxide, on the left-hand side here, if we add it to an aqueous solution, we see a change in pH equal to 5.7 pH units. If we look at it and we put the same concentration of the same species in a buffer solution, our change in pH is only 0.06 pH units. And this tells us that our buffer did our job, because a buffer resists change in pH. Okay, so in this particular case, we go through and we can do some stoichiometry with adding 1 drop of 10.0 molar sodium hydroxide to an aqueous solution. If we added 1 drop of 10 molar sodium hydroxide to an equal volume buffer solution, we see that we definitely resist a change in pH, and we can calculate that by using an expression. And since we have a ratio of A minus to HA, we can use moles that we add and moles that are neutralized in order to get these concentrations, because the volume values are going to cancel out here, and we're just left with a ratio of moles. So this example serves as an illustration of how effective a particular buffer solution can be at resisting changes in pH.